Did you do these alone or like with in your foursomes or with your partners? What that? Kind of different groups? Okay, fine. So in 43, we wanted to know, or we were told that waves are set along a spring of fixed length. And the first part asked, can the speed of the waves in the spring be changed? And then explain that. So Rachel, what did you and your group say for that one?
No, the speed cannot change unless the medium changes.
All right, so they said the speed cannot change unless the medium changes, and that's a pretty good answer. But didn't we change the speed of the waves in the Slinky last week? I think we did. We had to change the physical properties of the Slinky, and I think we did that by kind of reaching up and pulling more towards us so that the springs were had more tension in them. So it was difficult, but we were able to change the speed by changing the internal properties of the medium. But I actually am not at all bothered by saying that we can't do it without changing the medium, right? But maybe, depending on the medium, we can change it. And then in part B, can the frequency of a wave in the spring be changed? Will, what did you and your group say for that?
The frequency can be changed if you move the spring back and forth from right to left.
All right, so they said, yes, you can change the frequency if you move it back and forth more rapidly. Absolutely, right. So the frequency of the disturbance is the frequency of the wave, right? So you can change the frequency of the disturbance, yes. Any additional questions or issues with number 43? Michael?
Once the wave is formed, you can't change the
Once the disturbance is created, correct. You then cannot alter the frequency of the wave. Right, so once it's created, then we can't change it anymore. You're absolutely correct about that. Other issues with 43? All right, so Jack, we went over the quiz, which I'll get back to you, and we're going over the classwork problems from Thursday.
Okay.
Bits of my solution are still on the board. I don't know if you need to see it or not. All right, and then 44, what is the wavelength of a wave? Shri, what did your group say for that?
The wavelength of a wave is the distance between successive points of a periodic wave.
Distance between successive points, and what was the last part?
Of a periodic wave.
Of a periodic wave. That sounds pretty good. Yeah, the distance along the wave of successive points, or at least the same point on successive pulses. Yeah, that makes a lot of sense. And then we had 78, 79, 80, 81. I think I gave you my answers. So, but one of them I said not telling. So we'll talk about that, and then you can let me know if we need to see any of those. So 78, did we need to see, anybody need to see either part of that? No. 79, other than the not telling, did we need to see either part A or part B? No. All right. So for 79C, we apparently didn't have trouble finding the speed of the wave in water. We apparently didn't have trouble finding the period of the wave in water. Now the reason I wasn't going to tell you part C, the period in air, is that it's the same as in the water, right? Period and frequency are the exact inverses of each other, right? We just kind of said a minute or two ago that once you create the wave, there's nothing you can do to change the frequency. Michael reminded us of that, right? So as the wave goes, was it going from air into water or water into air? Air into water, fine. Right, so we have a boundary. Water into air, okay, so fine, so we can set it up that way. So we're sending some sort of wave energy from the water into the air. The speed can change, the wavelength can change, but the frequency has to stay constant because the only thing that controls the frequency of the wave is the frequency of the disturbance. So if the frequency stays the same as the wave enters exits the water, enters the air, then the period has to stay the same also. So you should have the exact same answer for C that you had for B, 1.00 microseconds. Other discussion about the frequency staying the same. Okay, again, the speed will change, the wavelength will change, but the frequency and period stay the same. All right, did anybody need help with any part of number 80? No. All right, and then what about 81? Yeah, all right. So at 81, we have a sonar signal, which is a longitudinal wave, and we send it straight down from a ship. It hits the bottom and is detected 1.8 seconds later. So I'm definitely going to draw a picture. Alright, so here's the water, here's the bottom, here's the ship, there's a sailboat, and then we're sending the sonar signals from just below the surface of the water. Right? So they're going down, they're reflecting, and then they're coming back up. What's the key word here we need to care about? Echo, right? Echo. So what do we know? We know the speed of the waves in the water is 1,498 meters per second. That's pretty fast. The energy's traveling for a total time of 1.80 seconds. Ooh, I did a bad thing, didn't I? Don't really want to use v there because it's not velocity. Let me continue to write the word speed out. We're looking for the depth of the water, but I can't find that immediately. First I need to find the distance that the energy traveled. Questions about my diagram or my identified variables? And if you wanted to cut the time in half, you could do that. Right, I'm not using that method, but that's valid. Alright, so speed is however far we travel, divided by the amount of time that we traveled for. So the total distance traveled will be the product of the speed and the time interval. So 1498 and 1.80. I did not solve these yet. So does anybody have that value for me, like already on your solution? No? How did we do it now? Do you know you have it? What is it?
2,696.4.
Can anybody confirm that? I mean, it looks right. It's a little less than double this, right? So that totally seems logical. So the total distance that the energy travels, right, down and back up, is 2,696.3. For the depth of the water, we're going to have to divide that by 2, right? And that should be, well, 1350, I think. Yeah, 1350 meters. All right, follow-up issues on that echo problem. Probably not used to echoes, in water, but that's exactly how we. That's how we find how deep water is. That's how we like little fish finders that tell you if there's like fish underneath your boat. They use that also. They listen for the echoes of the sonar waves. So any of you that kind of do boating probably know about that. I think that was it. Other issues about those problems from Thursday. Okay, so let's look at what we wanted to do next. So we went over the classwork, we gave back the quiz, we want to tidy up our wave features a little bit, and then we'll do a review of chapter 10 before we proceed with what occurs when a wave runs out of boundary. So we have a few objectives, but I don't think we're going to get to the last one. We want to relate wave amplitude to the amount of energy that's transferring through the medium. We want to describe how waves either reflect or refract when they reach the end of a medium. And then I don't think we're going to apply the principle of wave superposition today. So we do need to talk more about amplitude. There were just a couple of other things we wanted to talk about to tidy up our wave features. And I think we mentioned this one already, but I didn't have slides for it. So some waves are considered mechanical waves, just like some energy is considered mechanical energy. And then if a wave's not mechanical, we call it non-mechanical. We don't have a fancy term for it. But a mechanical wave means that we do require a physical medium. We need molecules in order to send that energy, or in order to propagate that energy. So air, does air have molecules? Yes. So a mechanical wave can travel through air. Does the water that we just had for our sonar problem a minute ago, does that have molecules?
Yep.
Yeah, obviously, right? H2O. That has molecules. So mechanical waves need molecules to travel. But some waves can travel through a vacuum. Some waves can travel even if there are no molecules at all. We call those non-mechanical waves. Can anybody think of an example of a type of wave that can travel through a vacuum? 3 of you? That's it? 4 of you? Brian, what are you thinking of?
Light,
Brian's thinking of light. What is your evidence that it can travel through a vacuum?
the sun.
Oh, so there's a vacuum, there's no matter in between the sun and the earth, but yeah, light can get here, right? Even today when there's cloudy and stuff, there's still light getting there. Yeah.
Ultraviolet.
Yeah, so all of our electromagnetic radiation can travel through a vacuum, so we call that a non-mechanical wave. Any other examples anybody knows of? Good. I don't really want to address the other examples. Now, what's that? Well, X-ray, that's other electromagnetic radiation, right? So X-rays, infrared, gamma, microwaves, whatever, all that stuff. Now, there's another way we can think about mechanical versus non-mechanical. For a mechanical wave, we need a contact force that's pushing or pulling on the medium, right? So on the slinky, we needed to grab onto the slinky and physically push the molecules of the slinky, either forward, backward, or right, left, in order to get the energy to travel. For non-mechanical waves, we're not using a contact force. We're not doing direct pushing or pulling on the vacuum, right? There must be some other method of getting that energy into the vacuum. Other questions on the distinction between mechanical or non-mechanical waves? All right, I thought of something else about your quiz when I was just thinking about pushing or pulling on the slinky. For generating transverse waves, I said right or left was the only good answer. Some of you said up-down. Why didn't I like up-down? Why didn't I like up-down for generating a transverse wave on the slinky? Will, what do you remember?
Because, like, if you just flipped it up, it's okay at that point. When you go down, it can't travel through the ground, so it stops at that point and it can't produce a full wave.
Yeah, when we tried, I think Brian did try moving the slinky up and down. Maybe I'm remembering wrong. It worked out okay at the beginning, but then the transverse wave never really reached me because, yeah, we can't get below the equilibrium position. We can't get through the floor. So ideally, we can generate a transverse wave by going up and down, but not on the slinky, not if we're holding it against the floor anyway. I really did only want to hear right and left. All right, then the other wave feature we wanted to tidy up a little bit was our wave amplitude. And remember that amplitude had a kind of different meaning depending on if we were talking about transverse waves or longitudinal waves, right? If we have transverse waves, then the amplitude was a distance, right? We said we can measure the distance between the crest and the equilibrium position, or the distance between the trough and the equilibrium position, right? We can measure those distances and call that the amplitude. Right? That's great, it's easy to diagram, it's not so hard to measure. For longitudinal waves, it was a little bit harder about it, because we can't just literally measure a distance. Right? For longitudinal waves, the amplitude is a measure of how compressed the compressions are, or how spread out the rarefactions were. That's not a distance, it's more like a pressure, a force per unit area, and it's not really something we can diagram very effectively, and it's actually not something we can measure incredibly well either. But either way, right, regardless of which type of wave it is, the amplitude is controlled by how much energy we're sending through the medium. All right, so if we send lots of energy through the medium, we're going to have high amplitude. If we're sending little bits of energy, we're going to have low amplitude, right? I'm talking louder than normal because I want my sound to show up on the video pretty well. So I need to get my larynx to put more energy into the air in order to get that higher amplitude, in order for more energy to reach the microphone on my camera. If you are surfing, right, it's going to be a lot easier for the water to change your kinetic energy if the water has more energy going through it, right? Like this tall wave. These short waves, right, you have to kind of cheat in order to be able to change your kinetic energy on a short wave like this, right? So how do you think I cheated there? I can think of 2 ways that I cheated. That is me. I can think of 2 ways that I cheated.
Is your brother the right photo?
Is my brother on the photo on the right? No, but this is in Hawaii, and that is where the videos were filmed. Okay, well the one way that I cheated should be a little obvious. I'm using a very different type of surfboard than the guys on the right. A longboard, right? So a longboard is much, can capture more energy from the wave because it's just longer, right? So it can pick up energy from a bigger, a more voluminous amount of the wavefront. So yes, a longboard was one way to cheat. And then what's the other way? Yeah, Ben.
You could put more energy by going sideways.
No. In fact, I don't think I'm not going sideways at all. So the other way of cheating was that I got energy from something other than the wave. Not a boat, but good guess. What? Yes. Yes, somebody pushed me. Right. Because there just wasn't enough, there wasn't big enough amplitude waves here for at least for me to get up. Somebody that knew what they were doing better could probably get up. I couldn't do it. All right, so those were just the two wave features that we did talk about, last time we met, but I thought there was a little more to the story. Other issues from anybody about mechanical versus non-mechanical waves, or amplitude being related to how much energy is traveling through the wave? Okay, great. So let's shift our gear slightly towards a chapter 10 review, but we can also go ahead and address the question that was up here when we came in. So I will, if you came in late, I'll spare you by not asking you. But I wanted to know, what is the unit of measurement of all of these different quantities from the chapters that our big quiz will be on. So let's start with work. Bharath, what was that measured in? Joules, that's right. That's right. How about power, Concha?
Watts.
Yeah, watts, good. And then how about energy, Meghna? Joules, that's right. And then period, Emily?
Seconds.
Seconds, good. And then frequency, Jenna? Hertz, yep, hertz. And hertz is the same thing as 1/seconds, but I am glad I heard hertz. That's the preferred quantity.
Sorry for the interruption. All the attendance sheets will be collected now, so please, teachers, if you could go in and double check and adjust the attendance sheet. Thank you.
We're just missing Kylie still, right? All right, what's next? Amplitude, Kat. Yeah, so amplitude, I should have put an asterisk here. So Kat said if it's transverse, it's measured in meters, that's right. And then if it's longitudinal, then it would be something like, newtons per meter squared, or something weird like that. All right, how about wavelength, Priyanshi? Meters, right, that's a distance. And then wave speed, who's somebody else that's been here the whole time? Amanda? Meters per second. All right, fantastic. Okay, good. So some of those quantities we first met back in chapter 10, in which we first heard about work and power and energy. Actually, all three of those. And then in chapter 11, we kept going with energy. All right, so, but work was where we started. And we said that work is a force times a displacement, but then we did need to account for any difference in the angle between those two quantities, right? Any difference in the angle between the force and the displacement. And we looked at a bunch of examples of assessing whether we were doing work or not doing work. So let's review some of those. All right, so here's my stapler. Am I doing any work to the stapler right now? No, it's not moving, right? It has no displacement. If we have a displacement of 0, then we're not doing any work, at least according to the physics definition of work. All right, how about if I gently lower the stapler at a steady speed? Did I do work then? No, I did not. There is a displacement, but my force was still directed straight up. Right? Even though I'm lowering it, we know that my force is directed up because it's falling, but it's not accelerating at 9.81 meters per second squared. It's not doing that because I'm still pushing up. So the force is up, but the displacement is down. Right? So those are opposite directions. Really, I'm doing negative work, but I think it's okay to just say, yeah, I'm not doing any work at all. Who is doing work in this example? The Earth, right? Because the Earth is pulling down, and we do have a downward displacement. So the Earth is doing positive work, I'm doing negative work. All right, how about now? Yes, now I'm doing work because the force and the displacement are in the same direction. How about now? I'm trying to move horizontally. Ooh, some of us don't remember. So which direction is my force? Yeah, I would argue still up. If I'm moving this at a constant speed, then I do not need a net force horizontally in order to do that. Right? So if I'm moving at a constant speed, my force is still up. Right? All I have to do is push those air molecules out of the way. It takes practically no force to do that. So the force is up, the displacement is horizontal, right? Theta is 90 degrees, the cosine of 90 degrees is 0, so no work at all. I did have to do a smidge of work to accelerate it to the constant speed, but after that, no work. And then I think the last one that I remember us doing was, what about this one? Am I doing work? Well, I am doing work, but yeah, I'm not really maximizing my work because the force and the displacement, they're not in the same direction, but they're partially in the same direction. There's a component of the displacement that is straight up. Brian?
Are you doing work when you're moving horizontally at like a not constant pace?
Is it speeding up or slowing down?
Speeding up?
Then yeah, because if it's accelerating, I am the agent of that acceleration. So I did have to exert a force in the direction that it's moving in order to accelerate it. So I am doing work, but it's probably not very much because there's very little resistance to that acceleration, so I probably don't have to push very hard. Unless it's really massive, like the stapler, no. But if I was able to like move this desk, right, I would definitely be doing work then because there's lots of resisting frictional force. So yes, if you push something heavy and you do have to worry about friction, you're definitely doing work. All right, so that was some review on just whether we are or are not doing work. You always should be using this equation, but if you have confirmed that the force and the displacement are in the same direction, sometimes we do take a shortcut and just recognize that this term is 1, but you can never go wrong using the full term. You can sometimes go wrong if you use that kind of shortcut. What else? And then we met power. We said power is the rate at which work is done. So if we don't do any work, then we're certainly not powerful. And then the other thing that I remember from chapter 10 was that a work is accompanied by a change in the form of energy, right? So if I'm lifting my stapler up, right, my work is going into increasing the gravitational potential energy of the stapler, right? And probably all of the work that I did ended up going into increasing the gravitational potential energy. If I slide this across the desk at a constant speed, am I doing work? I am, right? Because there is friction, and I don't think I can ignore it, even for something like the stapler. What form of energy is my work going into right now? Don't say kinetic, because the speed is constant. I think I heard it. Thermal, right. So friction's really good at creating thermal energy, right? Go like this. Right, within like 4 or 5 like periods, you can feel the heat, right? You can feel the heat. So friction's really good at creating thermal energy. That's what I remember from chapter 10. Are there any other questions related to work or power? Okay, and then again, chapter 11 was on mechanical energy. So we really mostly dealt with kinetic energy and gravitational potential energy, but I think we spent a few minutes talking about elastic potential energy. That would be unlikely to be a focal point on your quiz. All right, any other issues before we proceed into chapter 14.3, which is waves at a boundary? Okay, great. So here's a picture of a slinky. Now in this, what was it? My wife was like away the last 2 weeks, so I tend to let my son watch a little more television when she's gone than when she's home. And was it yesterday? Probably Saturday. He ended up watching like Looney Tunes, which I don't think he ever watched before, and he liked it. And it was Roadrunner part of the time, and then like Bugs Bunny and Yosemite Sam like the other part of the time. And it seems to me like this may have been taken in Roadrunner land. Why? Why am I saying that? What's the issue there? I mean, that's a slinky, right? It's attached to the wall. But Jack, what's the deal there?
It's like it's got tension. It shouldn't be like.
It should be sagging,
Yeah.
right? It should be sagging like a lot, and it's not, right? That's why we're generating our slinky waves on the floor here in Roadrunner land, right? We can delay the gravity. Usually the gravity doesn't kick in until we're like, a good 20 feet over the cliff, something like that. But this person was able to create a transverse wave by moving the slinky up and down. And that wave eventually is going to reach the wall. And then I can really only think of 2 possible things that could happen. I can envision the energy kind of bouncing off the wall and heading back, in this direction, or I could envision the energy going into the wall, or a combination of the two, right? So really the rest of today, or at least a good chunk of the rest of today, is on those two possibilities of the energy bouncing off the wall or going into the wall. And I think we kind of do we end at normal lunchtime today? Am I, yeah, or close to it? Yeah, I think it's like close to normal lunchtime. All right. So if the energy bounces off whatever our medium is attached to, right, our name for that is reflection. And I'm sure that that's a word that we're familiar with. If we think of like reflection off of a mirror, that's exactly like what we're talking about here, and that's a proper use of that word. If the energy goes into whatever our medium is attached to, we call that refraction. Is that something we've heard of before, either in chemistry or in like 7th or 8th grade? Yeah, raise your hand if like that's something you've heard of. I have a hard time believing that only half of you have heard of that before. It's a little bit unfortunate that the word refract or the words refract and reflect are so similar to each other, but I don't think we're going to have a big problem with that. Now, we're only going to talk briefly about these things today, but then chapter 17 is an entire chapter for the reflection of electromagnetic radiation, and then chapter 18 is an entire chapter for the refraction of electromagnetic radiation. So we're just going to do some cursory treatment today, and we're going to go back and really do some quantitative analyses of these things. Now, a little bit of terminology before we go play with the slinky a little bit more in the back of the room. So here we do have a slinky, and we have a longitudinal pulse traveling through the slinky. I think the arrow is supposed to be showing us the direction that the energy is traveling, right? So we produce the energy over here, we push the slinky forward and backward, and the energy is traveling towards the end of the slinky. We refer to the wave before it hits the end as the incident pulse, right? So it's headed, it has not reflected, it hasn't reached the end of the medium yet. And then as soon as it reaches the end of the medium, if it reflects, we call it the reflected wave or the reflected pulse. And then, well, if it goes into the other medium, we would call that the refracted pulse, but whatever. So here, right, we have incident pulse heading to the right, incident pulse still heading towards the right, incident pulse still heading towards the right, and then it hits the end of the slinky, and at least some of the energy, it looks here like most of the energy reflected off of the end of the slinky headed to the left. Questions on what we're seeing there before we go to the back and take a look at some transverse pulses? All right. This is, I guess we could film this. All right, so come on back here. Yeah, it's not going to be perfect. So all right, again, you're going to want to be able to see the entire stretch of slinky. Somebody take it, please. Thank you. Okay. Yeah, so there's no way that like half of you can see the whole stretch of slinky. If I put my face down where my hand is, I'm not going to be able to see most of you. You can come on this side, go behind Emily's a great place, next to Rob here's a great place. All right, whatever. So Emily, can you send me a transverse pulse, please? All right, good. Try and do a little bit higher frequency. The higher frequency ones tend to reach a little better. Go ahead. Yeah, let's make it a little tauter up. Try that again. All right, good. That time it reached me way better. Was there any evidence of a reflected pulse? All right, Michael, what evidence did you see?
After it hit like where your hands are,
Yeah.
it started to come back.
Right, yeah. So Emily sent the wave to me, and I'll send one to her this time. And it hit my hands, and at least some of the energy came back towards me. Right, so some of it comes back. Does all of it come back? No, it looks to me like the amplitude drops off, like as it's hitting her. So some of the energy reflected back, but some of it, I think, went into Emily. Now I'd like you to watch her hands very carefully and see if her hands move. If her hands